All right, welcome back to another round of creating our parts for our USB to, our XLR to USB audio input project. I'm Rich, and thanks for joining us again. Today we're going to build yet another part. This one's going to be a little bit more fun than building these resistors and stuff. Today we're going to build our audio codec. And remember, its main job is to digitize the incoming waveform. So we picked a fairly full-featured one, this AKM 5701 16-bit converter, and it's got a phase lock loop built into it. So the one thing that I wanted to make sure that we did is make sure our voltages are compatible with each other. So as we scroll down through the data sheet, you want to look, if they have an absolute maximum, you can do that. But I usually, if they have a recommended operating conditions area, then that's what I do. And this thing will go up to 3.6 volts. That's good for us because I'd like to try to run this thing internally at 3.3. Lots of microprocessors are happy at 3.3, and that's perfectly compatible with what we need to do. So with that, let's start building our part. As usual, we start out with our mechanical dimensions, which are usually towards the back. And there it is. This is a quad flat no lead package, and it's the type of package you would see on a cell phone or something similar like that. So this is a little bit beyond what you can do with hand soldering. You have to use solder paste for this, but I've got plans to show you how that can be done. It does involve hijacking a toaster oven, but that'll be another project there that we've got going on to help build it. Or you can buy a reflow oven off of eBay. There's several places that will do it. So with that, as has become our custom, we begin in the library editor. Sorry if I've got a little bit of a cold. We're going to make a new package, and that package will be QFN 24. I do not have a GDEC part number for this one, so I'm not going to do that. But we will give the overall dimensions, which is 4x4. And now we're ready to begin. As always, we start on our zero width wire that I call TDocu, and I'm going to do a lot more on the command line than before. I used to click around and change the grid, but you can actually just do it by typing the words change grid millimeters point. Our basic spacing here is 0.5, so I'm going to set that up to 0.25, a stepping of 2. And those are our, whoops, I don't want change grid, I just want grid. Those are our basic commands. If you ever wonder, the help system on Eagle is very good. The tooltip tells you the name of the command. So like here's the rotate command. And so I could go up in here and just type rotate. And it'll tell you how to operate it and what all the names are, but this is really actually very good as we get into user language programs, which I really want to get us to later on. So anyway, on to this project. It's a 4x4 outline, so as before, -2, -2. Oops, I lost my wire mode. Let's try this again. -2, -2, square corner, +2, +2. And back again. Perfect. Now I can tell you that the pin 1 designation on this one's a little funky because this is clearly looking at it from the bottom. So just beware as you're looking at these things when the part gets flipped and stuff. The nice thing is all GDEC manufacturers, which is everybody, always use the same style of pin orientation. So pin 1 is the upper left corner, usually as you're viewing it from the top as it's installed on there, right? So I'm looking down on the chip as it's inserted. That's a top left is pin 1. Obviously, it can be rotated to bottom left, etc., but it won't ever be in a strange orientation like that. And then it always goes counterclockwise. I've seen one chip where they put pin 1 in the middle. That was a microchip part. I don't quite know why they did that. Anyway, our reference dot is our next guy. Remember, we set up our width for that to be something that's not 0. And we use our right-click commands to build us a nice corner, which has gotten out of hand for me, so let's try this again. Ah, got me again. Heh. All thumbs today. There we go, finally. Text. Set up our pretty font. And that gives me enough space with the normal size of 0.127. I like to try to stick with the same font size if I can get away with it. Okay. And now let's put down our pads. Now our pad widths are determined by mechanical drawing, obviously. And so we can see that it's 23 mils wide. I usually don't go much wider than that to keep it from rotating, as we've talked about it before. And a depth of, it looks like 0.4, so I'm going to call that 0.5. SMD, I'm going to start out with pin 1, which is down here on this one for some reason, but remember it's going to come over here, and then when you rotate it, it would be, yep, that'd be right. So SMD of 0.23 by 0.5. Pin 1. And just to be real clear on this, let's check and see if we have another form of confirmation for pin 1, because I'm starting to doubt myself. There it is. Alright, so this is the top view, and this gives me what I need to know. I want pin 1, and I want him right there. There are 6 pins, which means we will split down the middle. So there's the middle, halfway in between, 3, 2, 1. And I don't quite like how this is going, so I'm going to go to a finer grid. Three, 2, 1. And there we go. We got a nice little bit of overhang there. Looks good. Pin 1. 1, 2, 3, 4, 5, and 6. And let's do our copy paste trick that we used before. Whoops. I want to keep the top layer. I don't want my T-docu layer. Yeah. So what I'm going to do is group. And now I'm ready to copy. I set myself on the origin, and that's going to be my rotation point when I do this. Copy group. So now get back on the origin. You see I'm nice and lined up, and I'm just right-clicking to copy with a rotation. And boom, and we'll do it again. Copy group, boom, boom, and one more time for giggles. Okay, so I didn't use a rotate command because the rotate would have actually moved it, and I wanted to make copies of it. So now that we're all happy with that, we can go ahead and turn back on our documentation layer. And I'm ready to put down my ink. Change, actually it's just layer T-place. It's another way to change layers, and now I'm ready to do text. Or I can do change font vector 1.27 vector, change size 1.27 text. You can see everything's where I want it to be. So obviously I'm going to put this part to the outside a little bit. And I'm going to go ahead and give myself a little outline. The outlines are up to you as to how complex you want to make them, what spacing you want, and so on. There's not a big deal. I said before that we don't want our ink here to impinge on our copper, even though the board house would actually slice that out in their masking process and stuff. We don't want to make their lives more difficult than it already is. So there it is, and I'm going to use a slightly different symbol than I've used before. I'm just going to make a little polygon here and chamfer off the corner. Maybe a little bit more chamfer. And that should indicate to anybody who wants to know where pin 1 is. So now that we're ready to go here, I just want to run my package documenter, make sure everything looks good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, yada yada. Okay, now one thing that is missing on here, I should have done this, I forgot about it, is the thermal pad. And we're going to do the thermal pad just a little differently. The reason that we're going to do it differently is look at the size of this thing. It's a pad of 2.4 millimeters by 2.4 millimeters. Now that's fine. SMD 2.4 x 2.4. That's okay. I'm not worried about that. But, and I'm going to call him pad, so tick pad. That way the word pad shows up on my thing as well. Now I'm going to go ahead and edit some stuff on it. So there's a way to do it with the change thing, but I'm finding more and more that I like the info button. And I'm going to turn off a thing called cream. Cream is the solder paste, and I don't want it. Oops. I do want a solder mask, so that was what my oops was, but I realized that I'm perfectly fine. Now let's see what that cream looks like. Okay, so if you were building a set of boards with the you were also building a silk screen, sorry, not a silk screen, a solder paste mask out of stainless steel, then this would be the layer that you would choose for your Gerbers for that. But I've denied that, and you can see that these guys all have a, let's turn off the solder mask layer so we can get a better look at it, which is called stop. You can see all these guys have not only copper but another layer on them called cream, right? So we've cut out things exactly the size of the pin, and we've made a layer that just says this is a rectangle where some paste is going to go. But I didn't do that with this big fat pad, and the reason is a fat pad like this can get overwhelmed sometimes with all the paste. Unlike on the edges where it'll wick up on the edges, right, these edge pins, surface tension will take it out to the edge, and that's why we make our pads a little bigger, and it walks up the edge of the actual contact terminal there and makes a little toe or heel, as the case may be. There's nowhere for this to go. It's trapped. So I'm going to manually create. I'll do it using the polygon command just because I like that one better. It's the rectangle is me have always had a little trouble editing stuff. So I'm just going to make a polygon. Doesn't matter what its name is, but it does matter what layer it's on. So this is going to be called T-stop. Sorry, not T-stop. T-cream. Let's turn off T-stop again. Okay. And I'm on T-cream. And what I'm going to do is I'm going to actually segment it out a little bit. And I'm going to make 4 small squares. I haven't figured out exactly where I want to put them yet. Should have come prepared. Alright, so that's a filled in area. By the way, this gives you a good example of the difference between that and rectangle. Notice the rounded corners, and notice the perfectly aligned corners. Okay, so there's a little bit of difference there, right? The thickness of the pen that we used is a factor in polygons, but it's not a factor in rectangles. However, I have a heck of a time trying to edit this thing. I can't grab it by its edges, it just moves the whole stupid thing. So that's why I don't like using rectangle tool. And these corners are easy enough to make and stuff like that. So I'm going to make 4 of these. And I'm not quite crazy about how the width turned out, but that's okay. I can edit these. And nah, that's good enough. Okay, so what's happened here is these are going to smush down like toothpaste, and they're a fairly thin layer, but it does have somewhere for it to go. Now we sacrifice a little bit of that with some. If we don't make these big enough, we don't get actual good soldering, and so if this is a high heat part or needs to be a low inductance part, which on this it needs to be both, we might be rolling the dice. But I can tell you from experience that this pad's going to work out just perfectly for us. So no problems there. Right, so a little unusual thing for that particular pad. If you're doing a pad that has a big fat, you know, electrical ground on the bottom, a big large surface area part, you will generally want to do this. And most manufacturers, particularly ones of linear regulators, will show you a similar thing. I think if we look at one of the regulators that I've got in mind, then you'll see that the manufacturer actually calls that out explicitly to make this kind of pattern. So let's give ourselves a description. 4 millimeter, 4 by 4 mm, 24 pin quad flat, no lead, 0.2.5 mm pitch. With exposed pad. Safe. Now, don't necessarily be sure that this is ground. You have to be real careful, and I've been burned by that, and by burned I mean literally, you know, had my fingers singed because I connected something incorrectly. It turns out that that pin was not a ground after all. So beware. All right, let's get into our next favorite thing to do. Obviously, let's go ahead and rerun our. Oops. And it made a nice little pad for us. So good for us. And that said, let's go ahead and make our symbol, which is our next thing. So it's going to be called AK5701. And I'm going to call this ADC AK5701. New package? Sure do. All right, now let's start to organize our pins. I like these kinds of drawings here because they really do kind of show you the flow pretty well. So the block diagram in this case is pretty darn good. So I'm just going to start making pins. And all I do is type the pin command and set up my directions. Remember, this is not a supply, so it's passive. Swap level is set to be 0 because I don't want to swap anything. These are going to be a little longer. I have found that the short pin length is generally good for what I want to do. And I do want to see both pins. Okay, so the only thing I don't like about this is I don't like its left to rightness. I just tend to kind of think from that the audio input should, I don't know, for whatever reason, go on the right hand side. So I'm going to do that. And I'm just going to start with my ticks L, and I always try to match the manufacturer's name if I can. Sometimes with a processor, sometimes I can't do that, but usually I can. LN1. Right in 1, space, whoops, well, okay, so it auto-named for me. Whatever. Alright, let's give these guys some brains here. When I give them a little space because I know that they're going to need to get some extra room here. Alright, now let's start talking pins again, and I'm going to start with my data side. LRCK, BCLK, SDTO. Alright, so we got those. And I also have a couple of extra friends here for looks like for side chaining, right? EX LRCK. So it looks like I can get this thing to go to 2 places, huh? EX BCLK. I will probably not use this feature, so I'm probably going to stick it somewhere that I don't need it. Oh, neat. I think, we'll look in the data sheet, but I think that actually what I thought was chaining them together was exactly what it was. I can put multiple ADD converters on the same serial bus, and it'll select it in, because I'm seeing serial data coming in and coming out and stuff. So there might be some cool stuff out in this chip after all. Let's put our power supplies up top. VSS is, is a ground connection in our case. Oops. Power down. That's a control pin, so I'm going to keep him handy over here with the control side. What I'm making is kind of an analog versus digital and power versus control kind of line in the sand. Alright, so that gets rid of this whole side here. Let's do some more clocking stuff. CDTI. Come on. CBTO, CSM, which is, I believe, a chip select line, but since they don't give it an overbar, I'm not going to. CSP, an interesting one. Here's a clock, and I'm gonna shove him somewhere over here. I really don't want him to buy my analog stuff, but I'm running out of space here. Okay. MC. CKI. Oops, that's what happens when you double click too fast. CKI, MCKO, and we get some more power supply stuff, it looks like. VCOC, which looks like a oscillator bias line, so I'm going to stick him over to the side here because you can see he's got a resistor cap to ground. And a VSS. AVDD. Remember, in the MOSFET world, the drains are on the top. VCOM, I happen to know very well, is going to need to be here near the audio stuff because it's going to be very much a part of the analog supply set. So that's going to be a part of something possibly if we need to. And mPower. That's going to go near. I don't know. We'll put them near power down. I don't know what that one does yet. So I should have 25 pins, and I need a pad. Need to look at what pad is called. Here it is. Handling of unused pins. See, AKM is really good about their stuff, but the exposed pad must be open or connected to the ground. Good news for us, we're going to call it. We're not going to call it ground because they call it pad. So there it is. As you wish, AKM. In a later one, when we do the microprocessor, we'll start separating it out and showing you how to make these things a little less crowded. But you can see I've given myself just a really nice little space to work with here because I got all these flipping pins running around everywhere. Not too terribly complicated for power supplies. We only have 2 pins to worry about, and that's good. Also separated out my analog and digital grounds. So this guy's going to take up a little more space maybe than I would have normally. So we have our left and right clock, our bit clock. I'm going to move those guys all together. I want to keep my oscillator stuff, MCI and MCO, kind of away and by themselves. And I got plenty of room to do that, so there's no worries. Alright, looking good. Let's go ahead and wire it up. Our width is set to 0.07, 007. And we're on our symbols thing. We got the right wire bends. Oops. I think I'm about 10 times bigger than I need to be. Nope, too thin. Should have stayed with where I was at. Okay. Lastly, we add our attributes. Name goes obviously on the names layer. This is where my 0.07 comes from. Manufacturer part number always go on info. I probably should make them their own layer at some point in the future, but I haven't. And there we go. Some people will put them in the middle, and that's fine with me. I just haven't gotten in the habit of doing that. So there is one good looking symbol. All right, we'll start working on the part next, or the device. Again, AK 5701. Prefix will be U because it's a generic IC. And I'm going to change something here real quick. I don't like where the insertion point is. It's in the middle. So what we do, you can see this is the insertion point and it's on a middle pin. I don't really like that. So we'll just do a group move. I just hit group, move, right click where I want to be, move group, and there we go. Back to our device. We can move it again. Now that's good looking. All right. Let's start pinning it up. Hopefully I got all the pins. I've been wronged before, and I probably should have done a quick count beforehand. So we'll see if I was right. All right, VCOM. AVSS. I have a program for bigger ones that I've done with that. I'm really itching to get shown off with the cool stuff you can do with Eagle's programming language. I think it's one of its best features. Actually, is the fact that you can write these scripted languages and stuff. That's just really very handy, and it can be a lot of fun. mclock O. There's space. Usually you see mclock O and mci together. That's unusual. So okay. The datasheet says. The datasheet says. External LR clock. Oops. So here's an example of a happy accident, right? And all I gotta do is double click them again to do it right. External STDI, then external LR clock. Now I'm on pin 13, external B clock, MCKI, CDTI, C clock. Ooh. Uh-oh. We find the lost pin. Okay. We will skip that for a moment because that happy accident we can fix. CSN is on 17. PDN. Power. 2, LN2, 1, LN1, VCOC, CDTI, and pad should be pad. Okay, pad's pad. So what we got here is a naming problem. It should be called C clock, not CDTO. And I'm going to connect him because it doesn't matter, and I'm going to go ahead and fix him right now. So you notice because I'm in schematic mode or symbol mode, I don't have any pin names, so I got to do it by trustworthy eyes. Do properties. I could also do a name command. So CCLK. And there we go. Save. Okay, back to my pinout. Alright, so everything is wired up. The variant's happy. Everybody's happy here. Let's fill in some attributes. Let's look for the actual manufacturer's part ordering information. And it looks like the only difference is a lower, kind of an automotive grade temperature range, so I don't care about any of that stuff. And let's see what the digikey says. Cut tape, because that means I buy small quantities and I want the in-stock one. Copy, paste, throw in a price. I know this is Canadian dollars, but I always put one in there. Okay, and the I don't know, for the description, I'm just going to steal right off the top. You may wonder what a 16-bit sigma delta means. A sigma delta is a type of 80 analog to digital converter. And what it does is it actually is only a 2 or 3-bit ADD converter, but it samples really, really fast and then performs digital filtering to get the equivalent of 16 bits of data. And it actually the technique works very, very well. You can get really high dynamic range and really low noise floors out of there. So it works out real well for us. All right. Now, I forgot to check this earlier, so bear with me. Is there a schematic example? Here's our hookup. By the way, we'll use that later. I'm looking for an analog example circuit. Here's one. Okay, so M power is mic power. So I thought it was master power. That's good to know, because what I'm going to do is, while I've got everybody here, I'm going to move that pin to where it's going to be more useful. They've got it way up on the top here, and I think that that's a good spot for it as well. So now I've got a little room for everybody. Just like they've got a little extra mic bias line if we ever wanted it. I'm not going to use it for this project, but this is a good idea. Okay, and voila, we are now done-ski. Let's go back to our schematic editor that we were working on before. And that thing is ready to use. We don't have to do anything fancy schmancy with it. And I'm going to just go ahead and add it to the main audio compressor page. We'll see what happens. All right. Good news for us. Now, one more thing, since we'll go back and we'll do that power supply line that I was talking about before. I'm going to make two of them. Okay, so this first one's going to be called plus 3.3 volts, and we'll just make a pin. The direction will be supply, and make it a point. No visible anythings. And we used a triangle before, so I'm going to use a square. Just using my Alt key to get myself a little extra fine granularity. And we'll move things to symmetrify them. Oops, Alt key, not Shift key. Looks good. Looks good. A little text. And name that pin. Remember, the pin name must match the net. There we go. And then we also have to, of course, make a part out of it. Plus 3.3 V. Just need one part. And one attribute that says do not bomb true. Okay. Values off, soup for our prefix. And this guy's ready to rock and roll. And then we'll make one more, and we're going to do something just a little time savery. I'm going to start with 3.3, and I'm just going to do a copy. We did this in an earlier episode in the package builder, and we just do a cut. We cut from our insertion points, and now I can make a new symbol called 3.3 VA for analog. Paste. Name. Change text. Sorry. 3.3 VA, and we're gonna have to fill that in, but I can't do that actually with a set of wires. I have to do it with a rectangle or with a poly. So let's come up with a new symbol. I want to keep filled in ones for like negatives, I think. So here's a symbol. It's kind of like a strange looking arrowhead. I think that's sufficiently different from the 3.3 volt one. Maybe make him a little pointier. There we go. So everybody should be good. And as we get into the layout of this thing, I'll tell you why I like to have my power supplies different from audio and not. Okay, now we're done with that. And now I've got a 3.3, which is going to be for digital. So that's good. And it's also going to be, this is an analog component, so I'm going to keep the SSM 2337. And you notice that I did my stuff right because it actually tried to connect that to the 3.3 volt rail, which has nothing else connected to it, but good on us for doing that right. Sometimes I will change grounds too, and I got to think about that on a project this small. For this one, I probably won't put two different power regulators, but I might put an inductor or something like that in the middle. Who knows? Add ground. And I think I am going to do that while we're making parts. Here real quick. We're making, I'll make a symbol for ground. I'm just going to steal him because he's so close to what I want. Cut. like a new symbol called a ground for analog ground. Occasionally, I may even make a third ground called chassis ground sometimes too. Oops, name. It's gonna be a ground, and we'll give him a different signal. So this guy's gonna look like a little triangle-looking thing. There we go. And now we can get rid of save. Now we can get rid of some of these other grounds that are running around here. Add analog ground. You watch these guys give me all sorts of messages. When I pulled off that named part, they went and reverted back to their $N$ kind of naming system to show that they weren't still hanging around with that old ground. I don't know which ground they would like you to put to, so it looks like they want to go to all of them to go to the analog ground. They don't have a digital ground in this. So, all right, that'll actually make things easier. Make a copy. Add resistor. Let's see what we got on here. Oh, all right. Now what am I doing? I got everything I need over here. I spent all that time making these things look nice. Now you'll notice me doing here in just a second, I'm going to make some very small resistors, small value resistors, and I'm going to put them right in line with a couple of these pins here. And in particular, what's happened is, even though these might not be only a couple megahertz or so at their speed, they have really fast edge rates. Right? So if you look at the timing diagram of this thing, and you'll see rise time, those are very square, which means that they have a lot of high frequency components, and so you put a little series resistor in here to keep them from ringing. I'll talk about that at some other time. All right, so what was our example circuit? Would tell us what to do. You can see it wants a little 2.2 microfarad and a 0.1 microfarad cap between VCOM and ground. So let's give him what he wants. We'll just steal one from over here. Remember, these were the right size. I believe they're 0603s. Oh, size A's. That's not actually the one that I wanted then. Non-polarized 0603. Good deal. We will double check a little later on to make sure I can actually get those. There was one there. There was one here and one here. On VCOM to AVSS, which of course is going to ground, and between AVDD and ground, there was another pair 10U. So let's set our values. 2U and 0.1. Actually, I said I like to call those 100 ends. These are TBDs yet, so I don't want them to have a value. Otherwise, I'll forget that they're there and think that I already made that decision. Less than 0.1U. All right, well, I'm not going to worry about that one yet. See how this thing's fit nice because I added all that extra space. So that looks good. I don't need these pull-ups because I don't need the mic power, the bias line for it. So that's fine. And on our 3-volt line, we've got ourselves a 0.1 and a 10U. Alright, good enough. And on the AVDD line, we got something similar, looks like. Oops. Let's ground these guys out. Alright, it's looking good. It's starting to come together. Let's go ahead and put some nets to it. These are going to be our 3 main serial port lines. These are going to be our 3 main control lines, which looks like they are probably SPI. Make sure that guy's stuck. Okay, good. Alright, we're getting there. This project right here is just about wrapping up. Let's pick some values for a couple of these things. Master clock in is one of the reasons that we use that PLL chip. And power down, I'll put that under software control too. I don't really care about a lot of this other stuff. Alright, we're getting close to our time limit. I'm trying to keep these things down to an hour, and we're getting there. So labels. Oops. You can see what happened here is they were too big, so we do a change size, or better yet, just undo. There we go. Labels. See, it's got this little rubber band that hangs out, tells you where the flyout actually is supposed to be connected to in case you do something stupid like that. And names. Now, I'm going to hold off on that for just a second, and this is going to be LR clock. ADC LR clock. ADC BC, okay. ADC ADCS data, we'll call it. ADC power down. And ADC M clock. Now, you notice that these extra resistors have kind of a direction to them, right? Left-right clock is going to come out of here, bit clock is going to come out of here, serial data is going to come out of here, but the master clock coming in does not have a terminating resistor. This is called source termination, and so let's change the values to 33. Oops. Value 33. Alright, so that's going to snub that down. It looks like it's so small it doesn't do anything, but it has to do with impedance matching these traces. And either 33 if you want to be a little more conservative, which I do. On this one, I don't like to have a lot of ringing going on here. So, alright, we are moving right along. We have a nice power distribution starting to come together here. So both these are connected via analog audio and using digital or analog grounds. We'll show you in a little while later how you use those and stuff. And one more thing, I got just a couple more minutes. We're going to make one more part. I know it says you just can't get enough making parts. This is going to be a test point because look at all these extra pins that I don't know what I want to do with. Since it's the first time I'm using this thing, I don't know if I want them to work. But I do know a package this small, I'm not going to be able to hand wire anything. So I'm going to just make a couple of extra little parts here. So this package will be called test points 40 mil. Okay. And I'm going to use my regular pad command because it's going to be a drilled pad. And I'm going to set the drill to be 40. And I want it to be round. Pin 1. And then I'm going to, I don't do this for everything. 40 is one of the bigger ones that I will ever use. And it's not going to be the one I use for this one. But since it's not a part that ever needs to be assembled, I don't need to worry about the T-docu layer. But I do want some silk screen. Okay. Now this is going to create an electrically bondable pad. Okay, so that one's good. And I'm also going to make a test PT 5 mil. So this will be a much smaller one. Same thing, except now he's going to be much smaller. And I'm not going to give it any silk screen. This is just going to kind of live out there. It won't have a label or anything. These are good for small ones. So this is just the thing. Make some parts. And TP will be our prefix. Oh, I need to create a little thing for that, don't I? Okay, so another pin. And just gonna put a little circle here. Maybe not that big. Alt key, don't fail me now. Actually, you know what I'm going to do? I'm going to change this. Change the function and give it a dot. Change length. Okay, so what that did was it created a little dot for me. And that way I didn't have to draw a circle. Now, they all will have names. And that should show up on the schematic, regardless of if they have silkscreen on them or not. So, change direction to passive, but this definitely does not want to be a supply line. Alright, and now we can make a thing called test point, which we already started. Cancel. New, and it will be a package dash 25 mil. Something went wrong there. Went rogue on me. Oh, I know what I did. I was so concerned about naming it that I forgot to click on the right F and 1. Okay, there we go. Okay, good, good, good. Also a do not bomb. Okay. And now we have test points. One of them is small and inconspicuous, the other one's a little bit bigger. I've put silk around the edges of those two sometimes to make them more prominent. Anyway, add brand new test point. And these are going to be small ones. So okay. No resistors or anything like that. These are just going to get connected for convenience later on if, as we're working with this, we find that we don't have something wired correctly or we need access to something we didn't expect. These things are cheap. They only cost you drill time at the board house. Okay, just about done. Lastly, VCOC. Alright, so it has some recommendations for these things. And I'm going to just simply pick a range. I know that I get 48 megahertz from the USB clock in order to make that work, so I'm going to pick the 12. So as we go through the calculations there, I'll kind of talk more about what was going on there in that decision making. For now, I just want to get done. Oop, I don't want to name the net, I want to name the part. All right, save. It's coming together, folks. It's coming together. These will be our two lines, and let's start with what did I call it? Comp audio in? Comp out. Okay, now we've connected the results of this over here. You can see maybe my left and right convention that I was so proud of was not going to work out. So we can fix that. Oops, I don't want all that. There we go. So what I'm doing is highlighting the whole thing with the group command and doing a move and right-clicking or middle mousing, and that just flipped the entire effing deal. And now I have the same left to right convention on both parts. Audio is coming in now from the left, going out on the right. There we go. Okay, we're right there, just a minute past what I wanted to do. Let's take a quick recap of what we've done here. We've created a whole bunch of parts, but we have our two main audio components, two of the three. We'll talk a little bit next time about preamps, and we'll start building a phantom power supply. But next time we're going to get into a program called Spice to simulate what's going on with our phantom power generator before we commit it to circuit board and stuff. So that should be real exciting. It's going to give us a break from Eagle for a second, and we will do something new. So I hope you guys enjoyed this. Until next time,